Okay, so chapter 9, we're almost done. We're going to do something called Chi-Square, which is lots of fun. All the statistics we've done so far fall into a category called parametric. Parametric means that those statistics are done based on a known pattern. The data follow the normal distribution. The data follow the t-distribution. Whatever it is, there's a pattern to it. Chi-Square is a non-parametric statistical technique. That means that the data don't have to follow a specific pattern. And in fact, what we're doing is looking at the data so we can see if there is a pattern to them or not. So again, parametric, there's a known pattern, and the data have to follow that pattern before we do the analysis. Non-parametric means we're looking at the data to see if there's a pattern or not. But we don't have any preconceived notion of what that pattern is if there is a pattern. The interesting thing about the chi-square is if we look at a normal distribution, and I know that's very exciting to you, normal distribution looks like this. And if we do a standard normal distribution, this is 0. Now imagine that we take every number in that picture and we square it. So 0 squared is 0, doesn't change. So if we draw x and y axes that look like that, all the negative numbers are going to be positive, so we don't need the negative side. 0 squared is 0. Starts right there. 1 squared is 1. So it's going to start and go up. The numbers below 1 get smaller. The numbers above 1 get bigger. And so we end up with a curve that looks something like this. This squared looks like this. And this is a chi-square. Which looks the way it does because it is the square of a normal distribution. The big difference that causes us when we do this is that where the normal distribution doesn't have degrees of freedom, the chi-square distribution does. And it's going to be fun. So, suppose we flip a coin 100 times, and we get 55 heads and 45 tails. Does that mean because we didn't get 50-50 that coin is not a random coin? Remember that chi-square is this test of whether there's a pattern or not. Pattern can mean lots of things. If this coin mostly gets heads and has more heads than tails, then that's a pattern. If it's random and we can't tell at all whether we're going to get a heads or a tails, then it's just a random coin and there's no pattern. So we expect 50 of each. That would be no pattern. 55 and 45 may or may not be far enough away from 50 that we think it's actually different. So we're going to do this. We're going to start out with a null hypothesis. Same null hypothesis in every problem, and that null hypothesis is that the information is random. Remember, we want the null hypothesis to be the hypothesis that it's no different, that there's no difference. In this case, no difference means the data we collect are the same as if these numbers were random. So there's no difference between the numbers we collect in the real world and what the numbers would be if they're totally random. Then we have the alternative hypothesis, which is, of course, that they're not random. So again, it's non-parametric. In non-parametric, we let the data tell us if there's a pattern. Okay? So we're comparing what should happen if this is completely random and there's no pattern to it, as opposed to, or, it's the random pattern, as opposed to there being some specific kind of pattern to it. So we're going to create a test statistic. And the test statistic for the chi-square, and that's chi-square, is the sum of observed minus expected squared over expected. What does that mean? Well, I observed, yes, you already know my handwriting is bad. I observed 55 heads. I expected 50. Okay, and sum means I'm going to do this for each number, and I'm going to add them up. So it's 55 minus 50. I also got 45 tails that wasn't observed, and the expected for that is 50. Okay, so I'm going to take 55 minus 50, squared that, divide by 50. 45 minus 50 squared, divide that by 50, add those up. Okay, and there's a number of degrees of freedoms in the problem, and the degrees of freedom is r minus 1 times c minus 1. That's a matrix of the data. So I take my data, and I have 55, and I have 45. Okay, does that make sense? And I'm going to put that into a little box like it's a matrix. No Keanu Reeves. In this box, this is a column, and this is a row, and this is a row. So I have 2 rows and 1 column. Okay? As we keep doing this and you keep practicing, it'll make more sense. Right? If we had a box that looks like this, then we have 2 columns and 2 rows. So the number of degrees of freedom is r minus 1 times c minus 1. Well, r minus 1 is 1, c minus 1 is 0. That's bad. But if there's only 1 row or 1 column, we don't subtract the 1. We just leave it as 1. So this would be 2 minus 1, 2 minus 1, and this would just be the number 1 because we never use 0. And so this problem would have 2, I can't even do math. Must be something's rubbing off. 1 degree of freedom, right? This is 1, that's 1. Multiply them together. 1 times 1 is 1 degree of freedom. Okay? Pretty exciting, huh? So I flip my coin. I flip it. And this is what I get. 55 heads, 45 tails. I expected to get 50 and 50. Now, you see how I made the box here? This is such a beautiful box, isn't it? I made this box, and then I draw this slashy line through it, and I put the observed on top of the slashy line and the expected on the bottom. The observed on the top and the expected on the bottom. And this is how we do this. So now I'm going to take 55. I'm going to subtract 50. I'm going to square that. I'm going to divide by 50. I'm going to take 45 minus 50. I'm going to square that. Divide by 50. And when I add those up, that's my chi-square. So I'm always going to draw this box. Going to have the observed and the expected for each outcome. In this case, I only have 2 possible outcomes, heads and tails. So I have my 2 observes and my 2 expecteds. Okay? And I'm going to do some math. So, again, my null hypothesis is this set of data is random. I do my math. And I get the number 1. So chi-square equals 1. What does 1 mean? Answer, it means nothing. There is no meaningful interpretation of that number that we care about. Chi-square is 1. That means nothing. We have 1 degree of freedom. So we did the math. We have 1 degree of freedom, right? 2 minus 1, 1 minus 1, except when you get that, you leave it as 1. That's 1. We're going to find a critical value, which is 3.84 in the table, and we'll go look that up for in a second. But here's what that means, is here we are, here's 0. The chi-square looks like that. Actually, it doesn't look like that. That's a really bad picture, but ignore that. Somewhere out here is a critical value. That critical value is 3.84. Out here, again, is our old friend, rejection region. And back here is our old friend, acceptance region. So back here, we're random. And out here, we are not random. Okay? So where are we? Well, our chi-square was 1. So we're here, 1. We're in the acceptance region. We're going to accept this hypothesis. And that tells us that the coin is random. Oh, look. Here's an even better drawing. So, kind of still a bad chi-square, but ignore that. There. 3.84. 1. Here's 0. Rejection region. Acceptance region. Random. All right, so given this now, we are going to go look. I do not want to keep my notations. We are going to look at the chi-square table. So here's the critical values of the chi-square. Degrees of freedom, alpha 0.05, alpha 0.01. Remember that 0.05 is 95%, 0.01 is 99%. At 1 degree of freedom, the critical value is 3.84. Notice something else exciting about this table. Where all your other tables, the big numbers are at the top, and they get littler as they go down. On chi-square, the little numbers are at the top, and they get bigger as we go down. Okay, so very simple little table. Nothing complexical. Okay, so back we go. Let's suppose that we want to use this the way we might use it in the real world. So you're a statistician, you might get a phone call from a casino, or you might get hired by a casino, and you would do things like figuring out whether something is random in the casino. So I've been called, for example, this is, again, old days, they don't do this anymore, they don't call you, because they've hired our graduates. So all our econ grads who, are good at statistics, because econ grads are good at statistics. They get hired by casinos and they do a whole bunch of fun things, but one of the less fun things that they have to do is sometimes figure out whether something is random. So in the old days, before they hired their own statisticians, you'd get a call from a casino and they'd say, hey, we have a big wheel, which is the big round thing in the casino that has all the different kinds of dollars on it. I don't know if you've ever been in a casino, but if you go to a casino someday, they have these things called the big wheel, which is a total ripoff. Don't ever play it. But it has different size bills running around the outside, and you're spinning. And they want to know whether that's random. Or they want to know whether a roulette wheel they have is random. And it turns out that the roulette wheels in casinos are generally not entirely random, and they actually do favor certain numbers. And in fact, before casinos caught on, gamblers used to go sit in casinos and watch wheels because they knew certain wheels would come up so many times so often, and they'd figure out what the pattern in the wheel is, and then they would start betting based on what pattern they saw on the wheel. So now casinos, knowing that their wheels are made of wood and aren't exactly random, randomly move the wheels around, and they actually have more roulette wheels than they have tables, and so you can't, if you're a gambler, you can't figure out where the right wheel is that you know what the pattern is on. So anyway, in the old days, slot machines had actual wheels in them, and the wheels had things on them. So you would expect that if there were 10 things on a wheel and you spun the wheel, that 1 in every 10 times each one of those things would show up. They have, the casinos, the old slot machines actually have weights inside the wheel, so they can make some things show up more often than others by how they weight it. But ignoring that, let's suppose here that we have a roulette wheel. and they've called you up and asked you to tell whether or not this roulette wheel is random or not. So you have the null hypothesis that it's random. That's the null hypothesis we always use. And you spin this roulette wheel or slot machine wheel 150 times. So we spin it 150 times. There's 5 things on this wheel. There's a cherry, there's a lemon, there's a bell, there's a paradise, and there's an economist on the slot machine wheel. We would expect, since we spun it 150 times and there are 5 things on the wheel, we would expect that each one's going to show up 30 times, right? We spin the wheel 150 times. There's 5 things on the wheel, so we would expect each one to show up 30. Well, what do we see? We spun it 150 times. We got 30 cherries, 20 lemons, 25 bells, 20 dice, and 55 economists. This is why this is boring, right? If you were the statistician doing this, you would have to sit there and spin that wheel 150 times. Usually, knowing that you charge by the hour, the casino would have spun this thing like 1,000 times before you ever got there, and they would just give you the data, and it would take you 20 minutes to tell them what they already knew, which is that something's wrong with it, and it's not random anymore. So we have a total of 150, and here's what's on the wheel. Okay? So again, chi-square is equal to the sum of O minus E squared over E. So we're going to take 30 minus 30 squared over 30, 20 minus 30 squared over 30, 25 minus 30 squared over 30, 20 minus 30 squared over 30. Okay, got that? So here's the diagram we're going to draw. It's a beautiful diagram. Nice little box. You notice it's got 1 column and 1, 2, 3, 4, 5 rows. Okay? So 1 column, 5 rows. So we observed 30 cherries, we expected 30. We observed 20 lemons, we expected 30. We observed 25 bells, we expected 30. We observed 20 dice, we expected 30. We observed 55 economists, we expected 30. So again, we just spun the wheel, and every time we spun it, we wrote down what came out, looked at that for 150 spins, and I said, of the 150 times we spun this wheel, 55 times that little picture of an economist showed up, and 30 times a little picture of a cherry showed up. Okay, so how many degrees of freedom do we have? Well, we have 5 minus 1 times 1 minus 1. Except when this happens, we just put in the number 1. So we have 5 times 1 equals 5. Okay? So again, we can pop out of here for a second. We have 5 degrees of freedom. At 0.05, 5 degrees of freedom, our critical value is 1107. So in this problem that we're doing, we have degrees of freedom equals 5, and our critical value is 1107, which is kind of Vegas-y, don't you think? 11 and 7. All right, so let's do the math. Again, 30 minus 30 squared over 30, 30 minus 30 squared over 30, 20 minus 30 squared over 30, 25 minus 30 squared. We do the math, we get 28.33. What does that mean? That means absolutely nothing. The 2833 means nothing. We had 4 degrees of freedom, didn't I? I lied. You should have told me I was lying. So our degrees of freedom is 5 minus 1. Twice I've done that today. You're just going to have to live with it because I'm not redoing this. That's 1. That's 4. 5 minus 1 is 4. You probably knew that. You were probably laughing at me. So we have 4 degrees of freedom. And our critical value is 9 point something. Okay? So change your notes. We have 4 degrees of freedom, and the critical value is 949. 28.33 is a lot bigger than 9.49. We reject. So let's look at the picture. Here's 0. Here's 9.49. That's my critical value. Here's 28.33 all the way out here. It's in the rejection region. Remember, accept means random, and reject means not random. Okay, so that slot machine wheel is not random. Economists are more likely to show up than the other. Okay, now does that mean the hotel would throw it out? Not necessarily, because they'd be able to calculate the odds now using that wheel the way it was, and maybe they like it and they'd keep it, because they're not really into fair in casinos. They're just into making money. Okay, that was good.